Good morning. Lecture 3, we will be covering, picking up from where we left off in the last lecture. We look at a quick summary of the key points that we have discussed in the last lecture, look at some examples, build on what we have talked about in yesterday's lecture, make another comment about the anti-aliasing filter used in the compact disk data example. And then today's focus will be on the reconstruction process and one of the applications of multi-rate signal processing or of DSP in general, where you can move the continuous time processing into the discrete time. So the last part will be the discrete time processing of a continuous time signal. So let us begin with the following task, a quick summary of the points that we discussed in the last lecture. I'd like to begin by pointing out that there was a mistake in the notes or what I had written in the class. I just wanted you to first rectify that. This was in the context of the Dirac delta. We talked about two properties of the Dirac delta function. The second one was the area property, the other one was the sampling property. And I just wanted to make a mention of a correction that you should make a note in your notes. So yesterday we did write down the following result: x of t multiplied by delta of t. Okay. So this gives me, this is the same as x of 0 because the function gets killed everywhere except where the delta function is non-zero, times the delta of t. Okay. This was fine, the way we had written it down. The second one was where we had made a error, x of t times delta of t minus tau naught. So this is a delta function, Dirac delta function positioned at t equal to tau naught. So you will sample x of tau naught, and this should be delta of t minus tau naught, basically the impulse response. In the class I had written it down and it is not delta of t. Okay, the delta actually occurs, the position of the Dirac delta does not change, the only thing is that it samples the function there. Okay, the second point or the other aspect that we had discussed in depth was that we are trying to sample a continuous time signal. So the sampling part comes by multiplying the continuous time signal xc of t with a impulse of a train of Dirac impulses, and this is the sampling function for which you have to specify the sampling period. And the analysis was that the time domain, we have the easy representation, straightforward representation of uniform sampling. In the frequency domain, xs of j omega. Notice that I have not yet moved over to the discrete time, so it is still the continuous time Fourier transform. This would be equal to a multiplication in the time produces convolution in frequency. So 1 over 2 pi xc of j omega convolved, this asterisk is a convolution symbol, s of j omega. Just mention that this is convolution. Okay. And we wrote down that this finally results in the following expression: 1 over Ts summation k equal to minus infinity to infinity xc of j omega minus k omega s, where omega s is the sampling frequency, or omega s can also be written as 2 pi by Ts, where Ts is the sampling period. Okay. And we did observe that there were three elements of our sampling process. The first one was a scale factor, the other one was multiple images, and the shifts happen as multiples of the sampling frequency, multiples of sampling frequency. And all of these are going to be exploited in our use of the sampling process. Okay. So that was the sampling process. Let me revisit the example. in order to introduce a new element that, that I want you to pay attention to. Okay. Again, it is the same example, but this time we will be revisiting it with 3 times to add something new each time. So, look out for what the new element is and make a note of that. So, we looked at a continuous time signal xc of t, which was cosine 4000 pi t. So, if I were to treat it like a using the continuous time notation, cosine omega naught t, omega naught, if I write this as omega naught is equal to 4000 pi, okay, 4000 pi. And we said that we would sample it at Ts equal to 1 over 6000. We will sample it at 6000 hertz, sampling period will be 1 over 6000, and this gave us x of n is equal to cosine 2 pi by 3 times n. Now, up to this is very straightforward, just substitute the sampling frequency and you will get this result. Okay. Now, here is a point that I would like you to note. So, the continuous time frequency is, if you think of it as cosine omega naught t, the units of omega naught would be radians per second. Okay, radians per second. Okay. Now, on the other hand, if I wrote this as a using a slightly different notation, cosine omega naught n, that is how we would represent a sinusoid in the discrete time. Now, the discrete time frequency is cosine omega naught n, units of n is samples, actually not, basically it is a dimensionless quantity. So, but if you want to take cosine of something, it has to have radians as the units. So, omega naught in this case has got radians as its unit. Okay. So, there is a difference between the what we call as continuous time frequency and the discrete time frequency. Again, this is something that I am sure you would have looked at in the context of DSP, but I just want to be sure that, so basically this is a dimensionless quantity. Okay, it is just a number. So, therefore, omega naught n, for it to have radians, this one omega should be. And if so, now if you were to compare when you substitute t equal to nTs, okay. So, omega naught t, if when you substitute t is equal to nTs, what you get is omega naught Ts times n, of which these two terms combined become omega naught. Okay. So, the general overarching relationship between frequency in the continuous time and frequency in the discrete time is actually embedded in this example. I just wanted to highlight that. That relationship is that omega times Ts is equal to omega. I have to use the word omega both times, but this is the continuous time frequency which is in radians per second. This one is the discrete time frequency in radians, and of course, when you multiply omega times Ts, you get the dimensions correct. So, this is the discrete time frequency. Okay. So, this is an important element in our understanding and our interpretation of the results that we have. So, for example, we said that we had a frequency 2 pi, omega naught is equal to 2 pi by 3. Now, how do I convert it into the corresponding analog frequency? Omega naught will be equal to omega naught by Ts. That will be equal to 2 pi by 3 into 1 over Ts. Ts itself is 1 over 6000. So, that basically gives me 4000 pi. That was the result that we verified yesterday. Okay. Now, the second or one more addendum to the thing that we had discussed in the last class. So, another frequency, continuous time frequency, another CT frequency, continuous time sinusoid, that will alias to. Okay, the 4000 pi is what gives you 2 pi omega 2 pi by 3 cosine 2 pi by 3 n. That will alias to cosine 2 pi by 3 n. I think we already wrote down the answer. I just thought I would highlight that. So, this is a case where omega naught prime, we will write it as 2 pi by 3 plus 2 pi m. We chose m equal to 1. So, with m equal to 1, omega naught prime will be 8 pi by 3. Now, how do I convert it into the corresponding continuous time frequency? We know the relationship. So, this gives me omega naught prime will be equal to omega naught prime by Ts, same sampling frequency. This is the one that actually produced the aliasing. So, this basically says it will be 8 pi by 3 into 6000, that will be 16,000 pi. So, a continuous time frequency of 16,000 pi cosine 16,000 pi t radians per will produce the same result as the case of cosine 4,000 pi t. Okay. And maybe a good idea for us to just confirm, or maybe you can do that as a simple exercise. Verify that cosine 16,000 pi t, when you sample it at t equal to nts, Ts is equal to 1 over 6000, then what you get is x of n is equal to cosine 2 pi by 3 n. Okay. So, obviously, we can see an example of aliasing, and there are infinite number of such frequencies that are going to map to cosine 2 pi by 3 n. So, therefore, the statement that was made is that the unique representation is valid only between the continuous time and discrete time, only if the Nyquist criterion is satisfied. Okay. So, if Nyquist criterion is not satisfied, let me give you the reverse condition. If Nyquist criterion is not satisfied, then there is no claim on uniqueness, not satisfied. Okay. And maybe there is even a further we can make a further specification that we are talking about baseband signals, because yesterday we said that there is a notion of band pass sampling which is different from the sampling of low pass signals or baseband signals. So, what we are talking about is in the context of baseband signals. So, if the Nyquist rate is not satisfied for baseband signals, not band pass, baseband signals, then there will be aliasing. So, the fact that the process of sampling is going to produce multiple copies is not the issue. The fact that somewhere if there could be an overlap of the images, and if you wanted to if you want to ensure that aliasing is not present in a baseband when a baseband signal is sampled. So, we have to employ an anti-aliasing filter, AA filter. So, if the sampling frequency was omega s, the anti-aliasing filter would be from minus omega s by 2 to omega s by 2. It will force the signal to be band limited, input signal going into the sampler, and therefore, you will not have the effect of aliasing. Okay. So, that is a useful result for us. Okay. So, the key points to remember are the sampling process, the creation of images, the aspects of aliasing. Again, this is something that we study very extensively in as part of this course, and we will come back to revisit it multiple times. Now, let me go back to the last slide that we looked at in the previous class. This was a case where we were trying to create CD, compact disc compatible data. So you had analog continuous time signal with information possibly up to 20 kilohertz. That's what we have shown here. It's got some range between 0 and 20 kilohertz, probably a lot of information in the lower frequencies, but there is a frequency content, so you have to preserve that. Now, if you wanted to sample it at 44.1, your anti-aliasing filter would have to be the one that is shown by the red line. And for an analog filter to achieve such a sharp cutoff would be difficult. So we said that multi-rate signal processing allows us the following option. Treat it as a sampling with a sampling rate of 176.4 kilohertz. So that means the sampling point has moved sufficiently far, and we now have the omega s by 2 at 88.2 kilohertz. The analog filter has to be flat up to 20 kilohertz and then can droop all the way to 88.2. Everyone's comfortable with that? After we have done the sampling process, that means you will have a signal where the green is present, and then there is some unwanted signal because your filter, anti-aliasing filter, allowed those blue lines to be, this blue component to be present. You have to get rid of that. So this then is followed by a digital filter. The red line becomes the digital filter. That will give you a spectrum at with a sampling rate of 176.4, which you then have to downsample to bring it to this form. This is the form in which it truly represents or is in the form of compact disc data. Okay. Now, a question that just want you to think about this. So here is a case where aliasing occurred, but aliasing did not cause a problem for us because aliasing, is the question clear? Aliasing is occurring here? Yes? No? No aliasing? My question is there aliasing in this process? There is no aliasing. Why? Because omega s by 2. Right, omega s by 2, what we did was that was sampled at 176.4, so no aliasing there. I am going to downsample by a factor of 4, but before that I applied a digital filter. So digital filter was, now my anti-aliasing filter is in the digital domain. So there are two, your final sampling rate of 44.1 came through two stages. The first stage was sampling at 176.4 kilohertz, for which the analog filter was anti-aliasing, no problem. Then you had going to be downsampled to 44.1, so which means that you must have another filter. If you did not have this red filter, what will happen? This blue portion will start overlapping with your spectrum. That is where the problem will come. That's where the aliasing will happen. Okay. Now, can I allow this analog filter to be a little sloppy, in other words, that it does not cut off at 88.2 but goes a little bit beyond 88.2. Okay, let me explain what I mean by that. Okay, so here is the drawing. Let's quickly reproduce the part of interest to us. Okay, I have the portion of the desired signal. Okay, and so this is 44.1. Sorry, this is 22.05. This is 44.1, 88.2, 132.3, and 176.4. Okay, so this is 176.4. Okay, and I have a copy of the spectrum because I'm going to sample it at 176.4. Okay, now the first option that we have done is an anti-aliasing filter which is flat in this portion and then drops off up to here. So no aliasing will happen in the process of sampling at 176.4. there is some unwanted signal that is present here. Okay, there is some unwanted signal that is present here, because this is a filter that will go on this side as well, go on this side as well. Okay. And when I do the sampling process, the images will be produced. So, there is some unwanted portion here, there is some unwanted portion on this side, all of that is present, and but the aliasing is not present. So, then when I apply the digital filter, it will remove all the unwanted parts, and then I get the signal that is of interest to me. So, now the question that is being asked is that I am going to have the same scenario, and here is the replica of the signal, that is when I sample it at 176.4 kilohertz, this is where it is going to come. Now, if I allow my analog anti-aliasing filter to be a little sloppier than before, what will happen? What will happen? It will allow more of the blue to leak, correct, and there will be the green will be present here, and when the copy comes, these two will overlap. See, there is a overlap which previously was not present, but now is present. Okay, is everyone clear with this one? Okay, this is aliasing, but has it affected your desired signal? No. So, in fact, you do not need to restrict yourself to this point, you can actually allow the analog filter to be even more gradual. Okay, now we get a little bit ambitious. How far can I go? How easy can I make it for my analog filter? Can I make it all the way to 132.3? How far can I go? It turns out that I can go all the way up to if this is 176.4 kilohertz, this edge will be 20 kilohertz away. 156.4, it turns out that I can go all the way up to 156. Before 156.4. So, I can go there because some unwanted stuff will come that will. So, basically let me show it in with. So, I go all the way to the maximum level possible. So, that means this orange filter is going to allow some unwanted stuff, and when I do the sampling process, that will be sitting here, but my digital filter will take care of that. Okay. So, the digital filter will take care of that. Notice the orange stuff is removed in the process. So, one of the things that I wanted to introduce through this example, of course, one is that multi-rate signal processing is a very practical tool which you are using every day, whether you may not have realized it. But it is all about understanding the underlying framework of sampling, aliasing, what is my desired signal, how far can I allow the aliasing to come, all of that is a very, very important element. So, the comment that I would leave here for you to think about is that we always take advantage of digital filtering. Okay, so, that gives you a huge advantage when you do, particularly when you are working in the area of multi-rate DSP. We always keep in mind that we have a very powerful tool in digital filtering, because you can design more or less any type of filter, low pass, high pass, band pass, a differentiator, integrator, anything you can build as a digital filter. Take advantage of digital filtering. Okay, so, this also means that when you say take advantage of digital filtering, reduce your requirements on analog filtering, but you have to be very careful that you do not compromise on the signal fidelity, the signal in the range of interest. So, you can deliberately violate. So, there are examples like in your music players where you may be violating Nyquist criterion deliberately. but because you know the portion of signal that is eventually going to be retained, so you take advantage of that. Okay. So, Nyquist criterion can be violated, but you have to be careful with the way you do that, so that you don't lose the some of the essential parts of what we are trying to do.